Yes.
Finished the introduction that Professor Ananthanarayan did his postdocs at PRL Ahmedabad, University of Lausanne, and University of Bern. And then he joined the Indian Institute of Science, where he has been for the last 25 years. He is an expert in particle physics and quantum field theory and has over 100 publications in many topics, from supersymmetric models and grand unification models to mathematical physics and calculation techniques in field theory. He will talk about the scientific life of Stephen Weinberg today, the man perhaps most responsible for the way we do quantum field theory today and who passed away early this year. So Anant, the stage is yours.
Thank you so much for this invitation. I'm very pleased to be here, to be able to talk to our friends and colleagues at SMBOS Center. I'd like to begin by thanking Amitabh Lahiri for his introduction, and also the efforts of Dr. Rajiv Mitra and Shanandan Gangopadhyay and the office staff that have made all this possible. Thank you so much. So I'll have a slightly unusual way of giving this talk, more the way historians and others do it, that they read out their own written notes first. This is in accordance with the principles of Patrick Winston, who says that every one of us has only one language processor. So if I showed you what I'm going to read, and if I speak, you'll only be reading rather than listening to me. So for the first half of this talk, which will be mainly about the person or the man, Mr. Stephen Weinberg, and a little bit about his work and my own impressions about his work and how things hang together. Then in the second half of the talk, I wish to highlight very specific contributions of his. And I think there it would be useful for me to be able to show you my notes so that you can follow some of those things. So let me, with your permission now, start and continue what I have to say. So Stephen Weinberg is a very towering figure in theoretical particle physics, who kind of dominated the last quarter of the 20th century with his ideas, and he continued to work till the end. So even though he was not very active in research towards the end, he continued to teach, I believe, and also wrote several textbooks and amazing output. So he was born in the year 1933 in New York City and passed away in Austin, Texas on July 23rd of this year, where he held the Josie Rosenthal Chair in Science at the University of Texas. So his father was Frederick Weinberg, and according to Wikipedia, he was a court stenographer, and his mother's name was Eva, and her birth name was Israel, and she was a homemaker. So he had no siblings. He was a single child, and he was married to Louise Weinberg rather early, and they have one daughter, Elizabeth, who's a medical doctor. So actually, one doesn't know a whole lot about him. When I say the life of Stephen Weinberg, actually, there isn't a whole lot to say because he seems to have been a very private person. So only a little pieces of information that we have about his life, about his education and how he went through school. He was very, and probably he was a very serious person and kept to himself. But some of his colleagues knew him quite well, and every one of them actually highlights how hard he used to work. This is one of the striking features of his life, is really, based on very solid hard work. So he is one of the architects of what we call the Standard Model today, and the Standard Model is the bedrock on which we understand the elementary particle interactions. And he brought order to a large amount of experimental information, a lot of confusion that was there in the field. So in the year 2021, when we stand here and many things look very simple, we don't understand the kind of struggles that people like Weinberg went through in their early years of research, and they brought order to this vast subject when experimental information was pouring in from several particle laboratories across the world, mainly in the US in those days, because at that time, Europe was still recovering from the ashes of the Second World War. Now the theater has shifted, and for instance, CERN dominates elementary particle physics, at least in experiments. So it was very different in those days. So he shared the Nobel Prize in 1979 in physics with Sheldon Lee Glashow and Abdus Salam for the unification of electromagnetic and weak forces. So that's the key thing. So here I've already used a little bit of notion of unification, which is a theme that actually runs through his work. Here we have the notion of unification already when we say electromagnetic forces, and that goes back to Maxwell, who united the electric and the magnetic forces. So the work of Glashow, Salam, and Weinberg was to unite this electromagnetic force with the weak force. The weak forces are the subnuclear forces that we are accustomed to, for instance, what is responsible for nuclear beta decay and also for the decay of a free neutron. A free neutron decays to a proton and an electron and an antineutrino. So those are the weak forces. They are subnuclear forces, so they only operate at very small length scales. And so this was the structure that was found by Glashow, Salam, and Weinberg. And the forces themselves are quite different in the way they manifest themselves. The electromagnetic forces are infinite ranged, and the force carrier is a photon. And there's a relationship between these two. Whereas the weak forces are very short-range forces. That means that the force carriers happen to be very massive. And those force carriers today we know are the W bosons and the Z bosons, which are actually predicted by these three authors. So the citation for the Nobel Prize reads, for their contributions to the theory of the unified weak and electromagnetic interaction between elementary particles, including inter alia, the prediction of the weak neutral current. So that's the thing. So up until then, this so-called weak neutral current, which is for which the particle that is responsible, what we call the Z boson today, was a prediction. Its existence was a prediction of this electroweak model. Not only that, in the work of Weinberg especially, there is a relationship between the mass of the Z boson and the mass of the W boson. So not everything is free in their unified picture, but the fact that there is a relationship between the mass of the Z boson and the W boson is crucial, and they actually are related through what today we call as the Weinberg angle. So let me say a little bit about him, about the man. So as I said, he held a chair at the University of Texas at Austin, where he was a member of the physics and astronomy departments. So prior to that, over the decades, Weinberg had taught at Columbia University in New York, at the Massachusetts Institute of Technology in Cambridge, Massachusetts, and at Harvard University, also in Cambridge University, where he actually got the chair that Julian Schwinger had held when Schwinger moved to the University of California at Los Angeles. And eventually he left Harvard and moved to Texas, presumably just as Schwinger got tired of the cold weather in Boston and then moved to Los Angeles. So I think even Weinberg had been attracted by the warm weather in Texas, and probably also a salary about which there is a story. And then there's also an apocryphal story, it could be true, that Schwinger left behind a pair of shoes in his office. And that is to say that Weinberg was expected to fill the shoes that had been vacated by the great man. So that's the story. He got his early education in a famous school, which is called the Bronx High School of Science, which has a habit of producing several Nobel laureates. In fact, Glashow and he were together at the Bronx High School of Science. There were many others. I don't quite remember right now. Probably Rabi and even Schwinger may have been students of the school. Probably Richard Feynman. They were of a somewhat earlier generation, and probably Gell-Mann as well. So he got his bachelor's degree from Cornell University in 1954, which is in upstate New York. And he got his PhD from Princeton University in 1957. So you see that there is a 3 years here between his undergraduate degree and his PhD. Now that seems like a rather short period to earn a Nobel Prize, the PhD degree. But let me also tell you that in that 3-year period, he spent 1 year away from Princeton. He had been at the Niels Bohr Institute in Copenhagen. So essentially, he did his PhD work in 2 years under the supervision of the famous Sam Treman, who also had the habit of producing many outstanding students. So after that, he, I think, moved to Columbia University, where he spent a few years. So one can find information about these things in Wikipedia and many other sources. And he also says a bit about himself in his own autobiographical note that he wrote for the award of the Nobel Prize. So for a person of his kind of influence and reputation, the number of PhD students that he produced is not very large. It's of the order of about 11 or 12, something like this. And the names that one would find, well-known figures, include Claude Bernard, who is a well-known figure in lattice gauge theories, Orlando Alvarez, who has worked in gravity, John Preskill, who was first known for his solution of the monopole problem in grand unified theories. So that's the thing. This grand unified theory is also, Weinberg is one of the people who was one of the architects of grand unified theories, and also the application of these ideas of grand unification in the early universe. So this monopole problem arises in the context of the early universe and applications of quantum field theory in the early universe at the time of the Big Bang and soon afterwards. Then Bob Holdham, who's another well-known person in Technicolor models, and Cliff Burgess, the professor in Toronto, and Fernando Quevedo, who many of you may know from his directorship of the ICTP in Trieste. So what are the general ideas of Weinberg in the popular mind? What kind of a person was he? What was his impact? I think he is very well considered as a great scientist, of course, and he was also a fearless advocate of rationalism and an anti-religious crusader. I think that this is very important. There are many scientists who do not concern themselves with matters of society, but I think in this regard, Weinberg, he was always hammering away at the need for rationalism and looking at all kinds of phenomena always from a very balanced kind of view. And he fiercely fought religious doctrines and argued with all kinds of people. He was not afraid to do that. I find that interesting and impressive. So in a sense, he was undoubtedly the most influential physicist of his generation. And I would say that he was probably the heir to the influence exercised by Schwinger and Feynman, the two towering personalities in the era of quantum electrodynamics in the United States. Of course, there was also Tomonaga in Japan, but not much is known about him. But between Schwinger and Feynman and Weinberg, I would say that Gell-Mann was a person who kind of extremely influential person. Now, Gell-Mann also passed away about 2 years ago, and so his work was also pretty much in the limelight some time ago. But Gell-Mann actually more or less stopped working in elementary particle physics by the late 70s, I would say. So really, Weinberg was dominating for a long time after that. He's also known, I would say, for his very direct way of speaking and writing. And that's what makes him so accessible. His popular works, such as The First 3 Minutes, a couple of other books that he has recently written, such as Dreams of a Final Theory. These are all very popular. And he has also got these really magisterial textbooks that he has written as a 3-volume series on quantum field theory. That is, it's actually not quite textbooks, I would say. They're more like encyclopedic reference books that people use and they really want to understand something. And there's so much labor that has gone into this. It's really very impressive. So here is a person who, besides his own research, he has also explained the subject, always tried to put it in simplified things to the basic building blocks. That also was his philosophical approach. He was what you call a reductionist. He wanted to try to break down all phenomena to the simplest possible building blocks from which you try to understand the field. So this is really what drove his philosophy. And then there were debates about reductionism versus complexity and complex phenomena, collective effects. And of course, he does admit that in a system like superconductivity, it is collective behavior that, for instance, you need to understand, let us say, a phenomenon like superconductivity, which of course exists in man-made systems in the laboratory, in contrast to nature, where he is really trying to find the basic building blocks. He's also known for his monumental book on gravity and cosmology. Now, please note that that wasn't quite his field, but still he wanted to master this field, and his way of mastering it was to just sit down and learn everything about the field and to write a book. So that's his book on gravity and cosmology. So his main contribution to the standard model, this electroweak model, was to figure out what we call the Higgs mechanism into this model, which is based on a symmetry. So the Higgs mechanism is needed to make force carriers massive. So as I mentioned, the photon is massless particle responsible for the electromagnetic interaction, infinite range, in contrast to the weak interaction, which now sits in this unified model. So he figured out how to make this thing, how to put these two things together, and then to give masses to the force carriers of the weak interactions, namely the W and the Z, and the mixing among the various force carriers, and that's why it's called the Weinberg mixing angle. He also has theorems on a whole vast range of topics in elementary particle physics, most of which are covered in his books, actually. His early work was on what we call soft pion theorems. He also advocated the approach of phenomenological lagrangians, that even if you don't know what the complete theory is, if you know some of the symmetries of phenomena that you're trying to describe, you try to construct a Lagrangian which is phenomenological, which is motivated by the need to explain phenomena, even if you don't know the full theory, and use such phenomenological Lagrangians in order to study physics. Now, this is a very popular approach today, let us say at the LHC, where we are validating the standard model at better and better precision. And yet we are trying to look for signals beyond the standard model. So the approach that is often used is that of effective fields and phenomenological Lagrangians. He also has theorems on behavior of Green's functions in asymptotic regions, in energy and masses. And this actually motivated many other studies of strong interactions, of trying to understand what today we call deep inelastic scattering, and also to uncover the nature of the strong interactions. So far, I mentioned only electroweak and electroweak interactions. There's also the strong interactions, which is based on theory based on quarks and gluons, which came a little later after clash of Weinberg and Salam. But Weinberg's work was very important in driving research in that direction also. So he was also interested in unification, unification of coupling constants of the three interactions. And that is how, they established the notion that unification actually probably makes sense. He was also interested in supersymmetry. There are so many things. Another approach that he had, which is very important, is if he had a certain idea, he would always ask, what is the impact of this idea on experiments? How would it show up in, let us say, a particle collider? What is the signal for this particular idea? So this is the kind of thing. So he was not a person who worked in every single paradigm. He actually created the paradigms. Actually, when historians eventually assess his work and his impact, they will discover, in my opinion, that he was actually the person who created the paradigms. So these are the various aspects of his work. He was politically, I think, what you might consider as quite conservative. He was liberal in many aspects. For instance, in his approach to religion, he certainly did not agree with religious ideas, but he was what you might consider as a patriotic American who always wanted to, help his government. And he was called upon, I'm sure, on several occasions. For instance, during the Vietnam War, there was a think tank of scientists put together by I think I've forgotten his name, Marvin Goldberger, I think, who was later president of Caltech. He put together a think tank called JASON, which doesn't stand for anything. And many leading physicists were members of JASON who gave advice to the US government and US military how to deal with Vietnam and so on. So that's where he stood. And he also was an ardent supporter of Israel and is known for having boycotted some conferences because, in his opinion, those conferences were anti-Israel. So this is as far as his ideas of politics are concerned. And he didn't talk about it too much. So, but one knows where he stood on these issues. So I myself have heard him speak on two occasions. Once in Paris in 1998 at the. Let me stop here for a second just to see if everything is okay. Am I audible? Is everything okay? Amitabh, is everything okay?
Yes, sir.
Yeah. Okay.
Yes, everything is fine.
Okay.
Yeah.
Good. Yeah. Please don't stop me if somebody wants to ask a question or wants a clarification. So anyway, so I've heard him speak on 2 occasions. Once in Paris, 1998, at the Niels Bohr Symposium. Now this is interesting because Weinberg was known to be a rather reluctant traveler. But he did come to the Niels Bohr Symposium, which was organized at the UNESCO. I guess because he had spent a year at the Niels Bohr Institute, so must have felt a connection and therefore is willing to travel. And in his talk, he talked about the history of the field, but he made a rather strong statement. He said particle physics is the only subject at the frontier. Now, of course, this didn't go down very well with others who work in other branches of physics. And Walter Kohn, who was also in the audience, who was a Nobel laureate in chemistry, not at that time, but he won the Nobel Prize a little later. So he got up and said, look, there are many other fields which are just as interesting, and named a couple of examples. Then Weinberg said, well, why don't you just give us our donné? We are the people who work at the frontier. So then another person got up and objected to this and said, I have a question. And Weinberg said, well, I'm not taking any more questions. So that was his style. You know, he just spoke his mind. He didn't care whether the people in the audience liked him or not. I heard him again in 2009 at the Chiral Dynamics conference in Bern. So he had been special invitee. So he was the first speaker at this conference. So it was completely full, the hall, enormous lecture hall, and then they also had CCTVs in a couple of other rooms in the university building. And they were also full, which is kind of surprising because the presence of CERN in Switzerland already promises that footfall of Nobel laureates. But I think there's something special about Weinberg that he had that kind of a crowd turning up just to listen to him. So he said, well, I must thank you for having invited me today and not yesterday, because it was the Wimbledon finals and none of you would have been here since Federer was playing. So he also knew what was going on and could also sort of make fun of himself. So that was the second time I heard him. It was a very nice talk that he gave on the origin of phenomenological lagrangians and chiral symmetry, on which he worked and so on. There's one more thing that I think was very interesting, that you must have heard of the superconducting super collider, which was a project in the US, a very high energy collider with a center of mass energy of 40 TeV. That was the planned energy, in contrast to LHC today, which has reached 13 TeV, 13. So you see, this was 3 times that energy which had been planned by the US, but various scientists had to defend this proposal, even though the site was already selected and some of the scientists had already gone and a little bit of the excavation for the tunnel had started, but it was not yet funded. So Weinberg was one of the people who was called upon to defend the SSC, which, as you know, was eventually cancelled. So he said, I told a senator, don't you think it is important that we push the boundaries of science and that it is important to know the secrets of the universe and push the boundaries of knowledge? Something like this. Weinberg said, I remember his entire answer. It was no. So you see, even a person of Weinberg's influence was not able to really persuade the US Congress to do it. If it had been sanctioned at that time by the early part of this century, probably it would have finished all the explorations of supersymmetry, dark matter, all these things. So that didn't happen. So there is still work for us to do. In a sense, we should be thankful that the SSC was cancelled. Some time ago, he wrote an article from which I want to tell you a little bit, because there are some scientists also, some students also present in the audience. So he gives 4 lessons for students. It's a fairly long article, but I pulled out 4 points for you from this article, which I think is something that you should think about when you go through, your education as PhD students, postdocs, early parts of your career. So he says, physics literature is an unexplored ocean. No one knows everything, and you don't have to. So he's saying, please start doing your research. Don't wait till you have finished reading everything. And he also says that while swimming and not sinking, you should aim for rough water. This is, I think, a very important point that he makes. That is, he's saying, do not work on very safe problems. You have to go for rough water, in the sense that there are problems out there. Nobody really knows what to do. And if you want to make an impact, this is what you have to do. Then he says you forgive yourself for wasting time. So he says not everything that one works on can give results, but one must think. So it is also important to make several explorations in directions which are not necessarily the only direction, say, for your PhD. This is how your brain is also kept active. And then he makes a fourth point, which is something which you don't hear very often. This is his point of view. You may or you may not agree. So he says, you will learn something about the history of science, or at a minimum, the history of your own branch of science, how the various ideas came together. Not everybody believes this, but this is his point of view. And I actually share his opinion, but that doesn't mean that you have to. Physics Today, after his demise, published several personal reminiscences. People like Helen Quinn, with who he actually did this work on unification, for instance. John Preskill has talked about his personal reminiscences. So Helen Quinn says that, so they had applied renormalization group to these gauge couplings of the three interactions. And then they found that these interactions, these coupling constants, actually do seem to meet. So that is where the notion of unification comes from. It's not just the group theory mathematical aspect, but also the dynamical physical thing and application of the renormalization group. So apparently when Weinberg heard the news, he was very happy, and he invited his collaborators home and opened a bottle of sherry and shared it with them. So there was also a human touch to his activities. So I do hope that the students here will make enough scientific advances during the PhD days that their advisors will, feel like opening bottles of sherry and sharing it with them. There have been very nice obituaries written for him. I'll just give you a couple of excerpts from some of the obituaries that I have over here. I will share the screen now so that you can have a look at what I'm trying to say. A window. Okay, let me share. So this I can share with you. Is it on? Have you got the share screen?
Yes, sir.
Okay, great. Okay, so one of them is from the CERN Courier. So here, this person who has written it, Gian Guidice, I think, wrote the obituary here. So here he says that when somebody said that you're a model builder, he said, no, I'm not a model builder in life. I have built only one model, and that is the standard model. Of course, because he had made such a major breakthrough, he is able to speak in this kind of, in this humble way. And it says that Weinberg's greatest legacy is his visionary approach to vast areas of physics, in which he starts from complex theoretical concepts, reinterprets them in his original ways, and applies them to the description of the physical world. He also actually writes elsewhere about his discovery of this particular issue of the Weinberg mixing angle and also the standard model. So he says that for a very long time, he was trying to apply these symmetries and the symmetry breaking to the strong interactions. So one day he was driving his car and he had pulled up at a traffic light, and then suddenly it occurred to him that the idea was correct, but he was applying it in the wrong place, that it should not be applied to the strong interactions, but it should be applied to the electroweak interactions. And then he immediately sat down and wrote his paper, which was published in Physical Review Letters, and is the most highly cited paper in particle physics. So that is the record of the standard model which he established. Then his own employer, now please note that he was 88 years old and he was still employed at the University of Texas. It shows the kind of passion that he had. And I also read that he had actually taught even in the spring semester of this year. So he was tireless. So when he passed away, they didn't say very much, only bits and pieces that he had been in hospital for a few days. And no cause of death was given, but of course, at that age of 88, anything can happen. So it was a full life. So it has to be celebrated. And they say one of the most celebrated scientists of his generation, Weinberg, was best known for helping to develop a critical part of the standard model of particle physics. Now, in the second half of the talk, I'll tell you it's not just the standard model. There are so many other things. So this was in 1967 where he developed the standard model of particle physics, when he was only 34 years old. Then he continued to work. And what I find very important and interesting is that the Nobel Prize, which is often the kind of kiss of death for many scientists, because they just stop doing anything after that. They just start giving, philosophy, giving advice to others, and so on. He didn't do any of that. For him, Nobel Prize was just one more thing. I'm sure he was quite happy at winning the Nobel Prize. He went back to his work. And then this is the other obituary from a newspaper from his hometown, New York Times. So it's probably the best place to read about him. What your hometown says about you when you're gone would be the most important thing, right? So I just included this from the New York Times. And it again talks about the same thing. It talks about the standard model. And it also points out that he had a rare ability among scientists to communicate and explain abstruse scientific ideas to the public. He was a sought-after speaker. Now, this is the other thing. Even though he was a sought-after speaker, he didn't make himself that available. And I can understand, because he was very careful with his time. He wanted to do his scientific work. Otherwise, a person with his kind of profile would spend all his time moving around here and there giving talks. But there are many talks that is available on YouTube, which I think is a very important thing. So it's great fun listening to him. And also he speaks very directly. No, he doesn't use big words and doesn't use very complicated things. Just talks in a very direct way that any child can understand. So here he wrote several popular books about science, notably The First 3 Minutes. This first 3 minutes is a very important thing, and he wrote this in 1977. You see, if you go back to the discovery of the cosmic microwave background radiation, that was only about 13 or 14 years before that. So it was just being understood what is the cosmic microwave background radiation, which gave a solid foundation to the Big Bang theory, which of course you may trace back to George Gamow of 1948 or so. But of course, nobody knew is it really true, is it not true? Then after the discovery of the microwave background radiation, there were detailed calculations for primordial nucleosynthesis and all these things, all put together. So it was still emerging at that time. But Weinberg took it very seriously, and he explained this to the lay public in this book, where he talks about all these ideas. And that's one of the reasons why particle physics and cosmology are actually popular subjects, that people like Weinberg manage to explain to others what is going on in their field. So now I want to talk, this is more or less the second half of my talk. I will talk about many different important papers of his, which I think were landmark. It'll also bring out the way in which he created paradigms when he worked. Now, if a person has worked in a subject for 50, 60 years, how on earth do you, select the most important works? How do you identify the paradigms that they have created? So I took the help. It's a sort of a numerical help that I took from Inspire, the database for elementary particle physics, which has detailed citation statistics. Then I asked myself, is there a correlation between the number of citations of a given paper of Weinberg and the kind of impact that he had? So when I went through this exercise, I realized that, hey, this actually, organizes his ideas. Just the impact of his papers seem to have almost a direct correlation with how well they have been cited. So let me go down, essentially in the order of his most cited papers. Of course, I violate this rule from time to time because I can't go through all his papers. There are also aspects of these publications that I will point out as we go along. Okay, and in what phase was the subject in at the time that he wrote his monumental paper? Where was the field standing, and what is it that happened over there? So as I said, his most cited paper, the one that is based on the idea that he got when he pulled up at the traffic light in his red sports car. So one of my colleagues here has a red car. So I told him, you've already done half the work towards your Nobel Prize winning work. You bought a red car. I hope he's not stopping at every traffic light to find a great idea, but that's his problem, not mine. So anyway, so this paper is called A Model of Leptons. It's a very simple, unassuming title over here, which is published in Physical Review Letter. And these are my notes on this paper, that it was in this paper that he proposes what is the mathematical structure of the electroweak interactions, So let me just use this mathematical symbols, SU2 cross U1, special unitary group in 2 dimensions, and U1, which is unitary in 1 dimension. The direct product of 2 groups. And the electromagnetic interaction lies in one of the mixtures of the U1 generator of this SU2 and the other U1. Okay. Now, this symmetry actually was already proposed by Glashow much earlier in 1961. But Glashow, as far as I know, did not give a picture of how part of these force carriers become massive. The main contribution of Weinberg was to show that you can break the symmetry in such a way, that's the technical term that is used, spontaneous symmetry breaking, which is another very important theme in Weinberg's work. In his work, symmetry is a very important theme. The presence of symmetries in the knowledge of group theory, the branch of mathematics that deals with symmetries, is a very important organizing principle for Weinberg. So in this, he actually shows how you get this Z boson and the photon by mixing part of this SU2 with this U1. Not only that, he's able to show how some of these force carriers become massive through the introduction of the Higgs mechanism, for which, as you know, Peter Higgs got the Nobel Prize for predicting the existence of the Higgs particle. So it is a special technique in quantum field theory which allows you to give masses to force carriers. So that is what was done in this. Not only that, they make special predictions. By they, I mean Salam also, whose work was published later in the proceedings of a Nobel symposium. Now, okay, so Salam also has this idea of this Higgs mechanism in generating these masses. And it predicted the existence of this Z boson, which was hitherto unknown. At the time of Weinberg's paper, the Z boson was not known, and it made specific predictions for experiments. And this was verified at CERN by a collaboration. It's a bubble chamber experiment, which is called the Gargamel collaboration. Now, who is Gargamel? Gargamel is the mother of Gargantua, who's supposed to be a big monster in some of these European fables. So imagine the mother of a monster, how big it must be. It's a very big bubble chamber experiment in which the experimental signals of the existence of this neutral current were detected. Not only that, after the Nobel Prize of Weinberg, Salam, and Glashow, these particles were directly produced, the W and the Z bosons, and the mass relations between them, which are predicted by Weinberg. And there are 2 experiments which are called UA1 and UA2, standing for underground area 1 and 2, which later produced 1 more Nobel Prize for Carlo Rubbia and Simon van der Meer. His second most cited paper, according to Inspire, which was a bit of a surprise. I know that this was an important paper, but I didn't know that it was that important, where he gave this ideas of phenomenological Lagrangians. So this ultimately had to do with interactions of pions. And all of you know what pions are. They are particles that were predicted by Yukawa for the internucleon force. And they also carry information on the ground state of the strong interactions. These strong interactions have certain symmetries, which are also spontaneously broken. Now, I said that there was spontaneous symmetry breaking in the context of the standard model, but there, these are what we call gauge symmetries, in contrast to the strong interactions where they're called global symmetries. So when global symmetries are broken, you produce massless particles. If the global symmetry is approximate, then you produce nearly massless particles. And these are the pions. The pions are very light on the scale of the strong interactions, which is set by, let us say, the mass of the nucleon, which is roughly 939 MeV. In contrast, the mass of the pion is only 140 MeV, a much lower mass. They are nearly massless. So the interactions of massless particles associated with spontaneous symmetry breaking also can be described in a mathematical framework. There's some beautiful mathematics associated with that. And Weinberg simplified all this fancy mathematics and said, look, if you have a phenomenological Lagrangian, which has these symmetries, it will reproduce what you want. So in that sense, he had simplified this theory a lot, and it became the cornerstone for developments of phenomenological Lagrangians. and studying the interactions of pions at high precision. Now, this also has experimental consequences. Now, pion scattering lengths and all are measured. And it also has consequences for lattice gauge theory, because the lattice gauge theory program is actually probing the strong interactions on the computer. So it makes many measurements on the lattice, which ultimately need to be compared with experiment. So there is an importance to these phenomenological Lagrangians and interactions of pions when you compare them with results coming from the lattice. So that is phenomenological Lagrangians. In both these things I mentioned, symmetry, spontaneous symmetry breaking, this notion comes and goes all the time. I also want you to notice that these two are single authored papers, and this is something that you will observe with Weinberg. Most of the time he sort of works alone. So he came from an era where it was actually possible to work alone. Most of physics has changed now. It's all massive collaborations today because one has to know so much, learn so many techniques, use computers, do all kinds of things. But he still lived in an era where he could actually focus and learn everything on his own and solve problems on his own. A counterexample to what I just said is a paper that he wrote with Goldstone, whose name is associated with these particles, such as pions, which are called Goldstone bosons of spontaneously broken symmetries, Jeffrey Goldstone, and Salam. You see, he's collaborating with Salam already. This, I think, is in the year 1960 or so. These are all pretty young men at that time, you see, but you see, they were really on the ball at that time, working very hard on the frontier subjects. Now, by this time, broken symmetries were known in the context of BCS theory of superconductivity. The work of Landau and Ginsburg were known, but those are all, Philip Anderson, these are all known in non-relativistic field theories or non-relativistic systems. So, how So this was the problem that was addressed. You can actually get these massless particles. See, so I consider this kind of very interesting that these people immediately worked on this and realized the importance of symmetries and that of spontaneous symmetry breaking, whether it was global symmetries or gauge symmetries. So that, I think, was a very important paradigm. You see, the paradigms here established here by Weinberg and others is that there are mathematical symmetries of this type which are of great importance. This is today what we call Yang-Mills theory. Yang and Mills had proposed this in the 1950s. They didn't really know what it was good for. The notion of these symmetries goes back to Heisenberg, but Heisenberg also had global symmetries, while Yang and Mills promoted them to gauge theories, without knowing where they would find applications or without even thinking maybe there are no applications. It was just an extension of Maxwell theory, which is based on U1 symmetry to what we call non-abelian symmetries such as SU2. So Yang and Mills did not know what to do with it. They were more interested in the structure and a natural generalization in a sense. Apparently it was already sort of known earlier to Klein and Shaw. Klein, I guess, like in Klein-Gordon theories, and Shaw, who was a student of Salam, they also had these notions, but Yang and Mills are the ones who kind of made this really quite concrete. So bringing these symmetries into elementary particles physics in such a powerful way was one of the important contributions of Weinberg that is done here. It establishes the paradigm of gauge theories over here. Now note that at the time that this work was done, nobody knew whether such theories are renormalizable or not, which is an extremely important consideration for elementary particle physics. That a theory needs to be renormalizable to make it sensible. However, in this phenomenological Lagrangians paper, Weinberg himself departs from this idea. He says, look, maybe renormalizability is not such an important criterion. If it is not, it will mean that you have to introduce additional coupling constants. So he is introducing both paradigms of effective theories, which need not necessarily be renormalizable, but which will bring in additional coupling constants. In contrast to the previous model, as yet, not known whether it's renormalizable or not. But that was done by 't Hooft and Veltman later. They proved that gauge theories are renormalizable with and without spontaneous symmetry breaking. So that was the landmark. QED, quantum electrodynamics, which is a gauge theory also, but with only massless particles. Abelian theory is proved to be renormalizable already by Dyson and Feynman and Schwinger and all these people. So that was extended by 't Hooft and Veltman. And that's where we are today. We have a standard model, which is a gauge theory, which is renormalizable, which is being tested every day at the LHC. So anyway, so these are the notions that he's playing with. He's creating the paradigms of gauge theories, of phenomenological Lagrangians, and also spontaneous symmetry breaking in a very powerful way by proving theorems about them, that these are true in relativistic field theories. So that is one of the paradigms that he has in this paper. He also is very interested in unification. Now, here you have this SU2 cross U1. The strong interactions are based on yet another symmetry that we call SU3, which is a direct product with these two. These two are already a direct product, and then there's a direct product with a third factor, which is the SU3 of the strong interactions. Now, for some of you who are aesthetically minded, you may say, oh, this doesn't look very nice. You have all these different factors and, what is the choice? It looks arbitrary. Then you may say, hey, is there a symmetry that is so nice that it contains all these factors? So that's where the notion of unification comes from, that you find a nice symmetry, large enough, mathematically beautiful enough, where all these factors sit in very nicely. So that's the notion of unification, and spontaneous symmetry breaking of that unification symmetry down to smaller and smaller factors. Okay. Now, in such theories where you have unification, where these things may be present and they break, there are all kinds of other processes induced by the fact that particles are also unified into representations of these groups. Then, of course, then you may start saying, oh dear, if all these particles are unified, maybe one of them can turn into the other. Is there a problem there? If so, what is the laboratory signature of such a thing that these particles are unified? So here is one such paper where he proposes that you can have processes where a baryon may turn into a lepton. For instance, protons are baryons, whereas an electron is a lepton. So you may have a situation where, say, a proton can turn into a positron. Of course, we need to conserve electric charge because of the fact that there is an underlying unified theory, and these particles are all unified into representations of those mathematical structures. Now, no points for guessing where this was published. This was published again in Physical Review Letters, you see. So if someone like Weinberg sends a Physical Review letter, manuscript to Physical Review Letters, it's immediately published. If one of us tries to send it, it may be at least 25 reports later, you have a chance of seeing your paper in publication. But hey, that's life. We are not Weinberg, so we can't really complain. So I want to say here that you see, whenever he has these ideas, mathematical ideas, field theory, unification, he is asking himself, if that is true, how do I validate it in the laboratory? And that is a very crucial question that he asks. So he proposes that there are baryon and lepton number non-conserving processes in such theories. And he says that, look, attention is drawn to the importance of measuring mu plus polarizations. Something as, shall we say, as prosaic as this. He just wants to talk about measuring the polarization of muon. So he is also close to experiment. He always knows what experiments are doing, what are they measuring, and he's also trying to direct them and say, look, you look for this, you look for that. That is also the case, I think, in the discovery of the W and Z bosons, that there was an influence of the theorists with the experimentalists. They were talking to them all the time. Look for this particular signal at this particular mass, at this particular energy, and so on. So another very important paper of his is pion scattering lengths. Today, people think that these are all, it's all done and settled. Well, as I said, it's not quite true, because things like pion scattering lengths are those that you can measure on the lattice today, directly or indirectly. So you need to have accurate theoretical and experimental measurements of this coming from effective field theories or wherever. so that they will provide a benchmark for the lattice. So no points for guessing where this is published. Physical Review Letters, this is also one of the highly cited papers. And it actually systematized many of the ideas that were floating around in the strong interaction sector. Note that Weinberg is concerned with every single phenomenon that is going on during the time that he is working. He is concerned with the electroweak interactions, he's concerned with the strong interactions, he's concerned with interactions among particles that are a residue of the strong interactions such as pions, and he's interested in very directly measurable quantities such as pion scattering lengths. Now this has paved the way to effective theories which are now a very mature subject, and these are also measured at high precision at various laboratories. So that's pion scattering lengths. Now here is a paper he has with Larry Hall and Joe Lycan. I think Lycan was one of his students, not very sure. So this is one of the rare examples of a paper that has co-authors besides himself. Just want to draw your attention to the title of this paper, Supergravity as a Messenger of Supersymmetry Breaking. Now all of us have heard of supersymmetry. It's supposed to be a symmetry that's present in nature, where for every boson there is a fermion and vice versa. But of course, there's no experimental signature of this. So if they are not there, then if the symmetry is not there, what happened to it? Well, we will say that it's broken. But we know today that global supersymmetry cannot be spontaneously broken. There are sub-theorems which prevent that from happening. So the only way you can have a theory of supersymmetry that's consistent is to also include gravity, which is what is called supergravity. Then you have a sector of the theory where supergravity is broken, and then it leads to a large number of operators and particles which may be present and may be produced at high energy accelerators. So Weinberg is interested in testing these theories also. He is very fascinated with this idea of supersymmetry. He's also fascinated with the idea of grand unification. He has worked on it. He has produced gauge coupling unification. So he says, if supersymmetry is broken, how do we find it? So this is one of the important papers in which they give the plan, the roadmap for finding signatures of supersymmetry if it is actually present at some high scale, and how it manifests itself today in the world that we see. So in a sense, this actually provided the building blocks for the effective models of supersymmetric theories. So it's a very nice paper actually. If you read it, they again try to simplify everything to basic building blocks and make it accessible rather than very complicated mathematics that goes into supersymmetric theories. So I just made some comments over here. Although this paper, it's interesting that this is almost 40 years old. This shows that many of the assumptions of the minimal supersymmetric standard model are still in accordance with this abstract that I have over here. It's a very modern abstract, you see. These papers are written at a time when people were just grappling with these ideas, but you still see their vision, how clear their thinking is about this particular model. And even 40 years later, I think that this comes across as a very modern formulation, even though it's one of the pioneering papers in this subject. So everything that I've been talking about so far is in elementary particle physics. Now I will just, in the last few minutes of my talk, I have another 10 minutes or so. Okay, I'll just assume that I have another 10 minutes. So here is this other paper that I mentioned already with Howard Georgi and Helen Quinn, where they talk about the hierarchy of unified gauge theories. They talk about the unification of couplings. Here is a paper again in pure elementary particle physics. You see, there are many particles that are somewhat heavier than the proton and the neutron, which are found in various experimental scenarios. They're all there, they're established. Their masses are known, their widths are known, their branching ratios into various final states are known. But for Weinberg, each of these provides an opportunity to say something about a unifying framework, about the way in which the ground state of the strong interaction behaves. So he finds precise relations between spectra of so-called vector and axial vector mesons. So you see, the point that I'm trying to say is that his approach is very practical. It is driven by experiment. It is driven by the need of the day. But he is also thinking out of the box to bring order into the universe. For instance, this unified gauge theories, there's no experimental evidence for it except the 3 gauge couplings. But he wants to see, is there an order, is there a larger theory from which these things could result? So that's an idea also that he's dealing with. So here, physical review letters with Georgia and Quinn, his own papers and other physical review letters. Now in quantum chromodynamics, which is the theory of strong interactions, I've talked so far about his work in the low energy sector, where he's talking about pions, he's talking about spontaneous symmetry breaking, or he's talking about these vexed vector and axial vector mesons. But in a very dynamical theory, when particles are collided at very high energies, quarks are essentially liberated, but these quarks, which are produced in such a fireball, hadronize and produce what are called jets. So that is at the other end of the strong interactions of quantum electrodynamics, where particles, very highly energetic particles, are produced, and then they hadronize and then produce things that the laboratory sees as what we call jets of hadrons. Now, George Sterman is the world's greatest authority on jets, and Weinberg has a paper with him in Physical Review Letters. No points for guessing. So here they lay the foundations of how to analyze and study jets in quantum chromodynamics. Okay, so that's elementary particle physics. Now, here is an interesting paper for you all. It's called Infrared Photons and Gravitons. So you see, there's nothing left untouched. His sweep is so enormous, so general. So here he is talking, and again trying to understand physics from a very basic point of view. So he talks about things, quantum mechanics, what we teach in our QM1 and QM2 courses. We verify the conjecture of Dalitz, that divergences in Coulomb, scattering, etc. He also is trying to unite the behavior of photons and gravitons. He wants to try to get an idea that one should not think of Einstein gravity as being something very esoteric or exotic that you will not understand. No. There's a lot of mystique around the general theory of relativity. You know, in the early years after Einstein's theory, people like Eddington made statements like there are only 2 people in the world who understand relativity. So he's trying to debunk that anybody can learn and understand all these things. Of course, it is a harder subject than many others. He has a very practical approach to the interactions of photons and gravitons. See? And then, as I mentioned earlier, he also is very much interested in properties of field theory. Renormalization is one of the most important ideas that quantum field theory has contributed to mankind. First, you can trace it back to, say, Gell-Mann and Low, and also to Bogoliubov and Shirkov, Peterman and Stegelberg, who are the original authors of this idea of renormalization group, that coupling constants will run as a function of momentum. This is because of the fact that in quantum field theory, changing of energy means that you try to probe matter at higher and higher energies, and therefore more and more excitations that are present in an effective theory can show up. So this is the idea of the renormalization group, which relates phenomena at different energy scales, which was later, of course, taken to an even higher plane by Wilson. But he had his own approach to these things. And I'd also like to say what his abstract looks like over here. Just look at how simple the language is in this abstract. Unlike the Gell-Mann-Low and Cullen-Simanczyk equations, they can be solved for arbitrary momenta. That is his new approach. The solutions involve a momentum-dependent effective mass and is a momentum-dependent effective coupling constant. As simple can be. There are a few more papers on field theory, which I'll skip because I want to get to something else that he has worked on. He's also looked at Feynman rules for particles of any spin. So he later concludes that any spin beyond spin 2 is actually not very interesting. It's impossible to write down a theory of interactions for particles with more than spin 2. You can have a look at these 2 papers. Now, I also want to turn now to 1 or 2 other things which are not his main stock in trade, but where he wanted to apply his ideas to other fields. So here is a paper, Gauge and Global Symmetries at High Temperature. Where do you get such high temperatures? You get such high temperatures only at the Big Bang. So here is an application of elementary particle physics to cosmology, to the Big Bang. He has all these notions of idea of symmetries which are spontaneously broken. But he would also like to have a situation where these symmetries are again reunited. And in order to do that, he wants to imagine a situation where at very high temperatures, these broken theories can have a phase transition and the original symmetry is restored. So this is a paper that he essentially formulates how to take quantum field theory and formulate it in an expanding universe and go back and run the clock backwards to the Big Bang. So that is his application to cosmology. There are one or two other things that he did, which I find pretty amazing. He wrote a review article for Reviews of Modern Physics called The Cosmological Constant Problem. If you look in Inspire, it has more than 5,000 citations. Pretty amazing. So this is not really a field in which he works, but he writes the definitive review article on the subject. Not only that, he reviews 5 different approaches here. You see, that's the reason why he has so many citations. If he had just reviewed his own approach, then hey, who cares? He reviews 5 different approaches to the cosmological constant problem, and he garners 5,000 citations to that. The other things that he was interested in is he's also constantly learning. For instance, all of you know that string theory was first born in the 1960s in the strong interaction sector, where there's a property that was known as quark-hadron duality was known. And then Gabriel Veneziano wrote the paper involving gamma functions, which had this property. So that's the Veneziano model, the first paper on what today we consider as a foundation of string theory. Later, Nambu and Goto showed that the Veneziano amplitude can result from an underlying string theory, a string scattering. But the second paper on the subject of Veneziano model is written by Weinberg, and it is written along with Veneziano himself and with Adamollo. So this is what I wanted to point out. He knows every single thing that is going on in his field, and he is working on it, and he's getting results as a product of his hard work. I want to finish with 1 or 2 other papers. He's also interested in string theory, and he wrote a paper called Coupling Constants and Vertex Functions in String Theory with a very simple abstract that I have over here. So he says that he's able to compute some properties, vertex operators, in terms of a string tension and a single free coupling constant. See, look at the simplicity of the way in which he... And I think after Weinberg essentially dominated the field, the next person to dominate, having a massive influence on the entire direction of theoretical particle physics, was Edward Witten. So it's only fitting that Weinberg should write a paper with Witten. And I just want to end my talk with just pointing out this particular paper that he wrote with Edward Witten. The 2 prophets have written a paper together, which is called Limits on Massless Particles, where they give some properties about Lorentz covariant theories. So you see, after these papers, essentially he didn't write very many research papers, but he concentrated on both his anti-religious crusades and engaging with superstition and all these things, and also finishing his various books and leaving behind an amazing legacy in terms of his contribution to science. So let me stop here and see if there are any questions. I'm happy to take questions.
Many thanks for a fantastic talk, Anand. And are there any questions? Are there any questions? I have a short question. You said that Weinberg was interested in supersymmetry, but he also knew that supersymmetry did not have any physical, signature. Okay, he actually writes that in the introduction of his 3rd volume of quantum field theory. So, did he actually say anything important in supersymmetry other than the grand unified model?
Well, he had, I would say that he had several publications on the particle physics aspect of supersymmetry. He wrote one of the early papers on what could happen to proton decay. So proton decay ideas came in unified theories, And then, of course, he had supersymmetric unified theories. And one of the early papers on presence of dimension 5 operators that could lead to too fast decay of photons was by Weinberg. And then he proposed this thing called an R symmetry that could, R parity, that would prevent such operators from showing up in a phenomenological Lagrangian. So R parity is an idea that goes back to Weinberg. I guess the coupling constant unification, of course, it was done by Dimopoulos, Wilczek, and Rabi in SUSY unified theories, which is a supersymmetric version of the Weinberg, Quinn, and Georgi paper. So he must have been interested in knowing, and he probably thought if we build SSC, we can either validate or we can, rule out supersymmetric theories, things of this sort. In a sense, it's a playground. It's open for everybody. Nobody really knows. That's the way I think about it. Yes.
The other thing is that he does not talk about non-perturbative effects of quantum field theory in his book, and I don't remember seeing anything on the topic by him either. Do you remember anything like that? I mean, does he talk about non-perturbative effects?
See, I know that these so-called Weinberg sum rules, they are quite important in applications to various non-perturbative effects. I don't know the exact relationship between those two. For instance, even now in this hadronic light-by-light scattering contributions to the G-2, they have various diagrams and they have estimates. Then they always apply the Weinberg sum rules coming from that paper to these. I don't think he followed the Wilsonian ideas of renormalization group very much, as far as I know. I don't know whether even Lattice, he was very impressed by Lattice efforts. I don't know, maybe he was.
Okay, if there are no other questions, let's thank the speaker again. And
thank you very much. Thank you very much. I hope that was of some use. So, because
thank you, sir.
Here I would invite you for a coffee, but
yes.
if you're not here, everybody else.
Very kind of you. Thank you.
Coffee.
Thank you. Bye-bye.
Bye.